here I have two slides of kind of summary that you can take a look at. And then we go to the, I won't read them, you will see them in 1 hour on Blackboard. Okay, we are not yet at Tomasulo. Then the first way to do things better is to take a look at instruction level parallelism and to see what can you do in order to run faster. Oh. That was not supposed to look like that, but you know, those are the topics. Essentially, we'll not cover all of them today. We'll just talk about instruction level parallelism. I don't know why it's looking like that. Then, today it's standard to work in a processor which has a pipeline. A typical processor pipeline might have 5 stages. This is the MIPS pipeline, and then you have instruction fetch, instruction decode, execution, memory operation, and write back. Those are the stages of the pipeline. Now, in this way, what you can do is you can have a life of the processor pipeline, more instructions in different stages of execution. Then I have one pipeline, and I am injecting in the pipeline each and every cycle one new instruction. Then, in this case, I may have 5 instructions which are running in the same time in different stages of execution. Then I don't have 5 pipelines or 5 pieces of hardware. There is no replication of the hardware. What I'm doing is, because the processing of the instructions can be split in stages, each instruction is in a different stage. Then, while the latency of the pipeline is, let's say, 5 stages, the throughput, the ideal throughput, it's one instruction each and every cycle. Assuming that I do not have kind of troubles in the pipeline, like, you know, dependencies, data dependencies or control dependencies, which will stop me from pushing each and every cycle a new instruction. Now, this assumes now that I'm issuing one instruction at a time. I can also, if I have enough instructions, what I can do is, instead of issuing one instruction at a time, to issue more instructions at a time. And those are, you know, what we call multiple issues processors, where I have even larger parallelism. Now, there are 2 ways of doing that. I can do it on hardware. Then the compiler is completely unaware of that. And I have in my processor a certain mechanism which is looking at the instructions stream and is checking whether or not there are instructions available for execution, and it's issuing them in parallel. Let's say I have what is called an instruction pool, where I fetch instructions. In that instruction pool, I may have 1 kilo instructions present. With some smart mechanism, I am checking which of those are ready for execution. Which means they have the operands available, and I can execute them. They might not be ready for execution, and then I cannot execute them. Now, if I have a large window, I may be able to find more instructions which are ready for execution. I'm taking those, and I am executing them, and I'm storing the results. What is happening now is that, as opposed to the standard pipeline processor, where the instructions are always executed in order, I'm kind of jumping the order of the sequential program, because I'm picking from here and there instructions which I can execute. I may do that as long as I get the same result. That I should not damage the control flow of the program and the data flow of the program. That I am always processing with an instruction the right operands that I should process when I will go single issue, single instruction issue. And I'm not going banana in the program on branches and things like that. As long as I have that, I'm doing a good job. And due to the fact that I can execute more instructions in parallel, and now it's not only that I have more instructions in different stages of the pipeline, one instruction in each stage, but I may have more instruction in the same stage. If I have more resources, I may have in a processor now 4 ALUs, which means I can issue 4 ALU instructions in each cycle. That might be possible. And as I said, hardware is commodity. We can put a lot of those things. Now, the question is how to do it in such a way that you preserve the logical flow of the program, you preserve the data flow, and there are also other things like, interrupts and exceptions, which you also have to preserve. But we'll come to that a bit later. Now, there are 2 types of that kind of multiple issue. There is what we call the superscalar, which relies on hardware to solve this puzzle. Then at runtime, I'm looking at an instruction and I'm seeing what can I do, those, which means at runtime, I spend energy in order to do that classification, or I have a software, a compiler-based approach, where the compiler will pack instructions in, let's say, tuples of executable instructions in parallel. Those are the VLIW architecture. And we'll talk about those, but not today. Now, most of the processors that you know are kind of dynamic. They rely on hardware to do that execution scheduling, and you see there are some names there. The one which are like static, which rely on the compiler, they are mostly from digital signal processing. A very famous one is the Trimedia VLIW processor, which was utilized by Philips in TV and other kind of media processing. I don't know if they are still doing anything with television. Most likely not. Most likely Philips, it's only lighting and medical kind of things today. But in general, those kind of VLIW, they were pushed by Hewlett-Packard. They are kind of the inventors of that, and they are specific for media processing. Do you know why? No? Try to think. Media processing is embedded systems. What is specific about embedded systems?
Only a specific task is being executed. Only a specific kind of task is being executed.
Yes.
In desktop and servers, maybe different types of tasks are being executed.
It's true, but it's not relevant in this context. Yes?
Because it consumes more power and resources.
Sure. That
in the hardware.
basically, if I go for that kind of VLIW approach, I'm spending the power at compilation, and I'm taking advantage of the parallelism at runtime for free. Because in embedded systems, power and energy are crucial constraints. Then it's more effective, you compile the application, take, some energy, but on a desktop, and then when you run, you don't spend any energy. The parallelism is there, and you just take advantage of it, and you may miss some opportunities, because the compiler can see only things which are static and known at the compile time, while the dynamic arrangement will speculate on all the possibilities which may arise. Okay, now if we look at the CPI of a pipeline, there are a couple of components which are contributing. We have the ideal CPI pipeline, which is, one instruction, one cycle per instruction. But this is the idea. In real life, the situation is a lot tougher. It's always the case. We have structural hazards in the pipeline. And those structural hazards do not depend on the program. They depend on the pipeline by itself. Let's say I am having a 5-stage pipeline, and in the execution stage, sometimes I rely on a functional unit which cannot deliver the result in one cycle because I cannot pipeline it, or it's too expensive to do that, or there are many reasons why I may not be able to do that. That will create a structural hazard because I cannot push next instruction in that execution because the execution is busy. Regardless of how my program will look, the pipeline will determine that. It will say you have to wait a bit, which is one cycle or many cycles that I'm losing. You may also have a problem, a similar problem with a memory. Then if I have a memory which does not have ports, different ports for instruction and data, whenever I am writing the result of the instruction, if I try to fetch an instruction, I have a conflict on that memory, and I have to wait one cycle. Now you may ask yourself, why am I not solving those? I might solve them, but sometimes those solutions are too expensive and they do not make sense because those hazards occur very not very frequent. Then, the first 2 points, they belong to the hardware, to the structure of the hardware, the ideal and the hazards of the pipeline. But there are now problems coming from the program itself. And I have the data hazards because sometimes, and actually most of the time, instructions depend on each other, which is not a surprise because that's the way the logical flow of a program should be. You compute something, based on that something you compute other things and so forth and so on. Then there are data hazards which will stop you from issuing a new instruction because you don't have the operands. The operand is computed by a previous instruction and you have to wait for that operand to be ready. And you have control hazards which are of the same nature, but now it's about branches. I execute a branch and I cannot fetch the next instruction because I don't know where I'm going, left or right. I may speculate and I say I'm going right, and if I speculate well, I'm fine, but if I speculate wrong, I have to flush the content and return. Okay? Branch prediction is a very usual trick in modern processors and usually is working. But those properties of the program preclude the utilization of instruction level parallelism. Actually, they limit it. And it's very, I will return to but this is kind of a bit better. Because in a modern program today, we have blocks of instructions, which are, let's say, 3 to 5 instructions. We speak about simple instructions, like RISC instructions, like MIPS, now in this book. And after 3 to 6 instructions, you have a branch. Then each and every, let's say, 5, 6 instructions, you have to stop in order to solve a branch. You may stall or you may not stall, but if you don't do prediction, you have to stop. If you do prediction, you might be wrong. Then programs today are not really nice, continuous string of instructions with no branches. And they have a lot of branches. And this is actually giving a very little parallelism, instruction level parallelism available. This is due to the very nature of the programs. If you go for more complex instructions, you might have less branches and you may do more calculation in a basic block. But that one is creating other kind of problems. Now you see, initially we have complex instruction sets. Then memory technology improved, then we could go for reduced instruction sets. Now we are kind of returning to CISC. This decision is, based on that kind of thing. By the way, you all have, I assume, a laptop running on an Intel processor. What kind of architecture is that? It's a CISC or a RISC? It's a CISC one. But the inside it's also CISC? It's a strange construction because it's a CISC architecture from the programmer point of view, which is emulated in a RISC machine in order to make it faster. But there are other kind of, like MIPS, there are RISC architectures on both levels. Okay. Now, you see, due to that, the parallelism is limited. And this means that in order to be able to have more parallelism, you have to look in more than one block. And if you look at this program, which is a simple program which is adding two vectors, you can see that there is no dependency between iteration I and I+1. Then if I issue instructions from different blocks, I have parallelism. If I just look in the block, I can do that addition in parallel with the incrementation of I, but that's it. I cannot do two additions. But if I do what is called loop unrolling in software, which will increase the instruction count, I can process more iterations in one iteration, or I can deal with that at the level of the hardware. And I can do what is traditionally known as data parallel processing, SIMD, vector processing, which is something that modern processors have for multimedia applications. If you have a 64-bit architecture, you can do 64-bit additions, but you can also operate on vectors, and you say, okay, my video samples are 8-bit, and because my video samples are 8-bit, instead of doing one addition on 64 bits, I will do 8 additions in parallel on 8 bits, and this is data parallelism. I'm executing the same instruction, I'm actually packing the operands, and I do one addition. I have to do it in a certain way with cutting the carry propagation, because otherwise the result will not look good. But with not a very complicated hardware, which is doing 64-bit addition, I can do 2 32-bit additions, 4 16-bit additions, or 8-bit additions, which will allow me to adapt to the data structure of the application and get some parallelism in vector mode. Okay, now those are some ideas on how to improve performance. And depending what you are doing, you may have diminishing some kind of, control stores, data stores, and things like that. As I mentioned already, a good design should combine some of those techniques. Not all of them, but some of them. If you just do one, it's not good. And you have to remember, if we speak about general purpose processing, we have to do good on average and not being chance on anything. Okay, we'll discuss about some of those. Now, let us look at what kind of dependencies and hazards may happen in a program. Remember, in order to speed up the program, what I would like to do is to issue instructions in parallel and change the order. Now, here I have a simple example, and I have instructions which are producing output for the next instruction. Then the instruction J is dependent on instruction I if it's using the result of instruction I. Or I have a kind of loop when after some instructions there is a consequences on my instruction. Now if my current instruction is at storing the result in F4, I cannot do it before the load, because if I'm doing it before the load, I don't know what F0 is. I cannot do the next instruction, which is a store, F4 to a certain address, because I don't know what F4 is. Then, in this case, I have a real hazard, because if I change the order, this may result in a read after write hazard. Then I am changing the order of the execution. And then I'm processing the wrong data. This is a real dependency. Now there are other dependencies. There is a name dependence. You see, I have an add and a load. From the compiler point of view, you know, F0 is just a register. There is no data connection between F0 in the addition and F0 in the load, except that it's the same register. If they could have been different registers, but the compiler is confined with the number of registers, and that was the register that could use. Then I can execute the add in the same time with the load only if I protect F0 before changing it. Then if somehow, if I take F0 and I store it somewhere in the ALU and then start the execution, I can also start the load. Otherwise, if I change the order, I may do an add on the wrong value of F0 due to the load. Then this is not a true dependency, a logical dependency, it's just an artifact. Okay, and this is called write after read hazard. And you can also have the same kind of dependency. This is an output dependency. Then you have two additions which are using the same register as output. You cannot change the order because this may damage the evolution of the program. Now, the question is how to deal with that kind of dependencies if there is a way to do it in order to increase the instruction level parallelism. The compiler can do things, but the compiler is trying to optimize other issues. You know, it's trying to put all the operands in registers to avoid register spilling, and things are getting very complex. And then from the point of view of the compiler, this is a good code. From the point of view of the superscalar processor, this is not such a good construction. And I should try to deal with it somehow. Now, those are the three issues which are making my life difficult. One of them is real. The other two are artifacts. Then if I can find a mechanism to deal with them in a smart way, I can get rid of them. Now, bear in mind that hazards are properties of the machine organization, as I said. Remember I said that functional unit is not pipeline, I have only one port to the memory. And they may occur, hazard, due to that in combination with the program structure. Dependencies, you know, are just properties of the program. Now, in the normal processor, if I do not have what is called a forwarder hardware, I will have to all the time in order to avoid the read after write hazard. Which means that, you know, are you familiar with the forwarding hardware? You heard about it? No. Then the idea is that one instruction may execute after another instruction, and I'm using the result of the previous instruction. Now, the result of the previous instruction, it's available at the output of the ALU after the execution cycle. Now, I have two choices. One is to wait until the result is available in a register, then to the write back stage, and then to issue the next instruction. Or I can make a smart change in the pipeline, and I can start the execution, and whenever I'm going to fetch the code, and when I arrive to execute, the result of the previous instruction will be forwarded directly to the ALU before it's available in the write back in the register. And this technique can solve me some problems. Then it's dealing with that kind of, and that's the reason why, you know, normal pipeline processors do have that forwarding hardware. I think in the book there are some examples of forwarding in Appendix A. Okay. Now, then this is what I want to obtain, to identify instructions which are independent and to execute them in parallel, you know, in any order without damaging the program, the evolution of the program and the data flow. And even if they are dependent, I might have some kind of overlapped execution, as I said about forwarding. Now you see, this is an example of that loop. Now it's written in MIPS, and you see that there are a lot of dependencies in here. And there are some of them are true dependencies, some of them are not really true dependencies. And on this example, it's quite clear that if I look on more loops, more iterations, things will get better. Now, that was the story about the data. Now we also have control. And in control dependencies, I have to be careful when I move instructions. Even though they are not data dependent, I cannot move them wherever I want, because they have to stay in, you know, in the decision block. And any kind of reordering that I'm doing should preserve the evolution of the program. And you see, the programmer can do a lot of things here. And this is a way to write this decision, and this is another way. You see, I moved an instruction before the branch. Then I start with the assumption that the minimum is B, and then I do the branch. And if the branch is not taken, I already have the result. If the branch is taken, I will compute the result. I moved the mean equal B out of the control. This is possible in some situations, but most of the times it's not possible. And I have to be careful, because if I'm doing that, I may end up with then I'm saying this again because this is very important, and you know, repetitio mater studiorum est. You speak Latin, right? No? How come? You didn't study Latin in school? None of you? No? Not fluent? but at least to understand what repetitio mater studiorum est. Rehearsal is the mother of study. Then I'm saying it again, but it won't hurt. The goal is to go faster, but the main goal is to preserve the execution of the program in a proper way, then not to damage the control flow, not to damage the data flow. And by no means, because otherwise your application will go in the wrong direction. And we might be able to violate that kind of these control things. And there are processors which do speculative execution. Then I'm making, guess, and I'm saying, in this branch I'll go right, and then I will start executing on the right, and fetching instruction and going there, and then eventually I'm wrong, and I have to redo all the things in the other direction. This may help me if I'm right, but if I'm wrong, it will penalize. I'm not damaging the evolution of the program, but if there is an exception, an exception means that I have a bit, a status bit in the machine which is telling me something went wrong. Let's say I did a division by 0. Then it will be a flag which will say, you have a problem. And the exception will be treated by a special subroutine or a special function in my application or a special function in the operating system, which will look at the status of the processor, and depending on the status will decide what to do. Now, if I do speculative execution, the status of the processor would be different. Then I have an exception, and my exception will see the processor in a different status than it would have been if no speculative execution would have been done. And that can create a problem. And in here we talk about what is called precise and non-precise interrupts. Sometimes you need to have precise interrupts and to know exactly your status when an exception is raised. Sometimes having non-precise interrupts is acceptable. Also, changing the order of the instructions may end up in exceptions which are not that obvious to detect, as you will see a bit later. Okay, now talk about that. Now, this is the story that I was telling you about. You see here I have a piece of a program, then I'm doing a kind of integer addition, then I have the branch, and then I have a load. The load after the branch, from the data dependency point of view, can be moved also before the branch. Because if the branch will be taken, will have no effect. If the branch will be not taken, it will be executed like it would have been executed after the branch. And then I'm winning something. Then, at the first glance, what I see is that moving the load up will be good. However, I have a problem, because moving that up might create me a kind of exception in the memory. It's not always the case, but if it creates me an exception in the memory, I may have a problem with, wrong address, something like that. Then my program will behave in a different way. Then I am damaging the flow of the program by raising an exception, which I essentially should disregard. And then I have now two possibilities. If I'm doing that, I will instruct the processor to disregard an exception if exception occurs. Okay, now I kind of touched that with except with precise and imprecise interrupts or exceptions. As a programmer, you don't really see those. Okay, sometimes you may see them because you get an error. say you have an error, you divide it by 0, or you had an error, I don't know, you try to do square root of a negative number, or I don't know, you have the very nice segmentation fault message which nobody understands where it's coming from, you know, it's a very nice one. But from the point of view of the operating system, it's sometimes crucial to see the status, the real status of the processor. And if that's the case, you want to have precise interrupts, which means that whenever an exception will rise, the status of the program would have been the same as the status of the sequential execution of the program. Okay, then if you would run with no parallelism, that exception would arrive, would occur, and the status of the processor would be A. If you go on ILP, you play with the instructions and you get an exception, it's the same exception, the state should be still A. Now, in some cases, you don't care for that, and then you may allow for unprecise interrupts, and then you speculate. Some of the speculating instructions are changing the status of your processor, and you live with that in a certain way, which means your exception procedures should be adapted to that case. This is mostly operating system stuff. Now, we kind of touched this already because I asked you about the VLIW, the embedded systems kind of parallelism. Then the dynamic scheduling is good because it squeezes even the last drop of available parallelism at runtime. Then if there is parallelism, I'll take it. But it costs me hardware, which may or may not be important. I said hardware is commodity, but I'm still a bit concerned. Do you still why I'm still a bit concerned? Then I'm making the hardware a bit more complex. What could be the implication on that? Energy, and a part of that?
Heat. Heat.
Energy is for sure, because you know I'm doing more processing.
Yeah.
But somehow, even though I don't care for extra hardware, I'm a bit concerned of that. It's kind of contradictory what I'm saying, right? Because I'm saying I have enough money, I can buy a Ferrari. But still I have some problems with that. When I'm making the hardware more complex, I might blow the cycle time. Then I might have to redesign the processor and diminish the frequency and change the pipeline. And then if I do have that kind of fundamental consequences, I have to think twice. Okay, then efficient but cost energy and might have implications on the, you know, then the basic architecture may have to change a bit. The performance of it may have to change. At the end of the day, when I draw the line and I make the addition, I might win. And I might run slower, but because I have more parallelism, I'm doing better. Then the other one is brilliant, except that there are not that many, and not all possibilities are utilized. Then, that's the basic idea. I kind of touched it before. Then I look in the text. Okay. I call it text, but it's not a text in the standard sense that we read by humans. It's the text which is the program, the binary of the programs. And I'm taking a large chunk of the program and I'm trying to see which instructions I can execute in parallel. And in this simple example, you know, I have a division which provides me F0 as result. It takes a lot of cycles. In a standard processor, I should have to wait until this is ready because the next instruction depends on that. In a superscalar processor, what I can do, I can look ahead and see, there is a subtraction there where I have no business with F0, and I can schedule it ahead. It's like, you know, you are jumping the queue, which is not very nice when you do it in the shop, right? Some people do that. I find that really annoying. And I usually say, I was here too and I'm not that small, you know, they see me. Because some people told me, you know, I didn't see you. Okay. Then this is the principle, jumping the queue. And jumping the queue in such a way that you did all the things that we just discussed. Do not damage the data flow, do not damage the control flow, do not do mumbo jumbo with exceptions. Now, how do we do that? Okay, this is a kind of recap of what we discussed. It's already fresh in your mind and I will not read it. And I will just think about how to try to do dynamic scheduling, or I should skip it for next time because I skipped 2 minutes. Okay. I can give you back the minute. Right? You gave me 1 minute extra, then it's 2:29, and you have 1 minute bonus. Now, I'll talk about that next time because I will stop in the middle of it, and this is a very important part of computer architecture. It's about the invention of a guy called Tomasulo, which had a brilliant idea on how to implement this kind of dynamic scheduling of instructions in a very effective way. Before him, computers were doing the following. We are fetching the instruction, a couple of them. We are checking if there are enough instructions to be executed in parallel, and if they were, we are issuing them. But in the unexecutable one, there were also the artifacts. They're not real data dependencies. Then we are not really speculating enough on the available parallels. And Tomasulo came with an idea which is solving that problem on the fly. And he got an award from that, and it's a very elegant and simple thing, which most likely you will have hard time to understand from the book. Don't ask me why, because I did not understand it from the book. In the book there are examples, but it's not really focused on the mechanism in a proper way, for my taste. I hope next time you will understand Tomasulo from my story, because it's a fundamental concept which is applied today in modern computers. Okay, I'll see you next week.